If I try to elaborate this idea, this can go on like that. When a DC supply is a fixed amount of supply, so you have a fixed current or you have a fixed voltage over time, but that's a DC. And AC, on the other hand, has variable value. So you do not have the same value of current continuously, or same kind of value of voltage continuously. It is continuously going up and down. It is continuously fluctuating. So instantaneous heating effect for an AC supply is different. At some points you are heating up a resistor, or at some point your heating effect will be pretty strong. At some points it will be pretty weak, and so on and so forth. So if we want to have a cumulative amount of that heating effect, and we want to express that as equivalent to a fixed DC voltage value, we can get a much easy to work with equation format. For example, P equals to I square R, because the electrical power formula P equals to I square R, where I for AC is a variable. So if we can convert that I into some sort of a constant value, it would be easier for us to go for the power calculation and such. That's where the RMS value comes in. True, a graphical representation for the RMS values can be shown to be something like this. Is that if, have a look, let's say, let me zoom in. This is a normal I versus time graph, I or V, whatever. If you square this, the entire thing becomes much too bigger, and you have this shape. Now, whatever the area that you have over here, if you want to represent this same amount of area under this I square segment as a rectangle, you're going to have a certain height. Let's say this is the rectangle that gives you the same area as this amount of loop. That's basically what I square is. And if you root that this is I square, this is the I square or V square graph, and this is the I RMS square. So there is a integration process to calculate how this can be calculated, which I'm not showing you, but this is a graphical representation for where the RMS comes from. So technically speaking, the same heating effect of a DC current, which can be obtained from an AC voltage, that value of the DC current is the equivalent RMS current value of the AC supply, and same goes for the voltage as well. Mathematically, it can be derived to be of this shape, that RMS value equals to maximum value divided by √2, or voltage RMS equals to maximum voltage divided by √2. The typical value that we usually, when an AC source is quoted by voltage, usually the RMS value of the voltage is mentioned. For example, the supply in our households, which is about 220 volt AC, means the RMS voltage is 220 volt. So maximum voltage of the supply is going to be √2 times, which is 311 volt. So the voltage actually fluctuates from positive 311 to 0 to negative 311 to 0, and that keeps on happening, and the frequency is usually 50 hertz. That's how our regular line works. So that's how the maximum voltage is actually much higher than the rated voltage of a supply, which means if someone gets a shock, that shock would be more deadly than 220 volts. The maximum shock can be of up to 311 volts. For transformer calculation, both I primary and I secondary, or VP and VS, must be in the same expression. That is, we can either have the transformer equation in RMS format, or we can have them in maximum format, but not a mixture of those, which means we can have a ratio of VP by VS for RMS, or we can have a ratio of VP by VS of maximum equals to NP by NS. You know this equation from your O levels, that voltage and number of turns are directly proportional, whereas current and number of turns are inversely proportional. So that's what is shown up over here as well. So if you go for the current, that would be inverse. So current secondary divided by current primary, either you take RMS ratio, or current secondary by current primary, you take the maximum ratio. It is equal to number of turns in the primary divided by number of turns in the secondary. So it can work that way as well. And then we have this representation of graph. And the last thing that we have is eddy current. Did I talk to you about eddy currents ever?
No, sir. I suppose not.
Okay. So I'm going to go elaborate on eddy current. Eddy current is a pretty interesting thing. Before eddy current, I would like to show you something. I hope I can show you something. I believe I have that. I hope nothing weird pops up. No. Stereoids, nihilist magnet. Yep. No, not this one. You have seen this one already. Shoes, ultrasonic clean, period, orbital mechanics. No, not here. Where is my original 9K folder? Airplane engine, no movement, checkmate, calisthenics. খুঁজে তো পাচ্ছি না, এটা তো গতকালকে দেখলাম।
স্যার
দাঁড়াও, একটু ওয়েট করো বলবান। I was trying to show you something which I cannot find. Got it. Okay. Oops. All right. So you have, can you see it? Silicon sealant.
So I think we saw this one.
Yeah, exactly. I'm just gonna show you one more time. So this is just a piece of aluminum, and these are magnets which are about to get rotated. And there is a timer, there is a silicon sealant too, so that the water doesn't leak out. The water is in perfect contact with the metal piece, and he is gonna start rotating this magnet and see what happens.
How is this happening?
I'll explain.
Oh.
So yeah, there is more. Oh, there is more. Okay. So what is actually happening? Here's the deal. This is the effect that we call eddy current. The way eddy current works, I'll try and get some better pictures. My Windows bar gelo kothai? Why is my PC responding so weirdly? The icons are all messed up. What is this? I turned my TV shows from Crazy HD. Obvious.
AZTV, sir.
Crazy HD. It's a Bangladesh-based
HD.
BDIX torrent site. They have everything, literally. Okay. All right. Let me try and explain to you using this image. This is a pretty nice image, which can work for me. Do you have a simulation? If we have a fit colored simulation, then this would be amazing. No. Eddy current breaking system using EMS. Can we have that? Maybe not. Acha, never mind. Let me just explain. This is a metal disc, any metal, not essentially magnetic metal. It can be aluminum, copper, it can be iron, it can be anything. The more the N is the N in this case I mean as the electron transport equation N. Remember I equals to NAVQ. What was that N called? Anyone remember the term?
Number of field lines.
No. I equals to NAVQ. There was an electron transport equation, or it might as well be called the drift velocity equation.
Electron density. Electron.
It's called electron density. Beautiful. It's called the number of electrons or number of charge carriers per volume. So the bigger number of electrons that you have, the better. Anyway, this is a metal disk. This metal disk is about to be rotated in a vertical magnetic field. What is very important, that this magnetic field is affecting a very specific portion of this metal disk. It is not all over this place. This is an important bit. So try to understand what is going to happen as this disk is going to be rotated. So bear with me very clearly. If you have confusion at any point, you ask me about it. Think about, okay, let me just, can I have a 2D view of this thing? Oh, yeah. Same pictures. Achha, I'm going to draw it. Don't worry. So let's say this is a circular piece of metal that we have. This is the central shaft. I'm going to fill this shaft with, let's say, ash color. The whole thing is ash color as well. Problem there. Okay. So this is the metal disc. And this is rotating in anti-clockwise direction. So let's say this is the direction of the rotation. And we have a magnetic field that is going into the page for this much rectangular space. This much rectangular space. So we have a magnetic field, strong magnetic field that is going into the page. So we have North Pole on the top of the plate and South Pole at the bottom. Think about it. This thing has electrons around it. If you would normally rotate it without the presence of the magnetic field, the electrons would also rotate along with the disk, obviously. So whenever this disk is rotating, consider one electron of the metal plate, one electron. So let's say this blue spot is one electron. This electron is going to rotate and enter into the magnetic field. Now, try to understand, as the electron will enter into this direction, if the electron movement is happening in this direction, the conventional current is supposed to be in the opposite direction. So I'm trying to visualize a conventional current that is produced because of the physical movement of the electron, because the disk is being rotated. Do you understand my point? Try to visualize the whole thing in a much smaller scale than it actually is. The disk is rotating. Imagine there is a single electron on the disk. That electron is traveling from left to right into the magnetic field. So the conventional current produced by this electron should be from right to left. A2 point clear kina? The direction thing.
Yes, sir.
Yes, sir.
ঠিক আছে, এখন ফ্লেমিশ লেফট হ্যান্ড রুল ইউজ করে বের করো এই ইলেকট্রনের উপর ফোর্স কোন দিকে হবে। ইউজ ফ্লেমিশ লেফট হ্যান্ড রুল। First define your left hand and then try it. Aim your index finger into the screen. Aim your middle finger towards left, because that's the conventional current direction. So the electron will be pushed in which direction? Outwards or inwards? Towards the center,
outwards.
the periphery.
Outwards, sir.
Outwards, right? Do everyone get outwards? The force direction? Everyone.
Yes, sir.
So whenever the electron will enter over here, along with the rotation of the disk, this magnetic field is going to apply some vertically downward force onto this electron. So this electron will try to get out through this side. So if the electron is trying to get out through this side, there will be a conventional current that will be produced vertically, which will be in the opposite direction. Let me draw this with purple. So there will be some upward directional current that will be produced within this segment, because electron will be leaving out from the bottom. So conventional current will be happening in the upward direction. This current is the sole outcome of the presence of the magnetic field. Amra jodi magnetic field na ditam tahole kintu ei vertical current ta hoito na. This vertical current is existing exclusively because the magnetic field is there, which is applying some force on the moving electron as they are trying to pass through that magnetic field. And as the magnetic field is pushing onto those electrons, they are trying to move because of the effect of the magnetic field. Because of that, they are producing a current. So what's going to happen? Electrons are going to try to rush out through the bottom. So conventional current is going to be produced over here. Well, obviously there is not a single electron on the metal disk. There are a lot of electrons. So we're going to have a pretty high amount of current that will be flowing out of this space. So because current is essentially flowing out of this space, well, we can say that for this region of electromagnetic space, let me zoom in a little bit. For this region of the magnetic field, we can say that the lower side is a high potential side, and this is a low potential side. Can you say that? Because conventional current always travels from where? From high potential to low potential. So this current is going to go up there, and eventually they are traveling in this way. Actually, আমার এই সাইনটা দাও আসলে ঠিক হইতেছে না, because এখানে potential নিয়ে কথা বলতে গেলে আবার ভেজাল হবে. So disregard the potential sign. Conventional current is coming out through this side. This current, so what is happening? Electrons are leaving from the bottom. So this might actually produce a void of electrons over here, but no space in this metal piece. It's a sea of electron, will essentially remain void of electron, which means electrons are gonna fill in from the top as well. So if I try to represent the direction of the movement of the electrons are gonna come out through the bottom. I'm showing it with green, and they are gonna go the other way around where the magnetic field is not present, and eventually they are gonna fill up this gap. Because naturally they are going to try to have the whole electron distribution equal. They cannot exist. They are pushed down over here because of the presence of magnetic field. So they're being pushed downwards, and they're going to go through the other part of the metal piece where there is no magnetic field, and they're gonna have this. This will produce a very significantly high current within the metal piece itself, because we are talking about mobilizing a vast number of electrons through a conductor that is practically a metal. This entire metal disk is a conductor. The number of electrons available is pretty high, and we are forcing all of those electrons all together. And depending on how fast this disk rotates, the force will be determined onto this fact. So if the disk is rotating really fast, the force on the electrons will be very high, and the current will be also very high. And as a result, the electrons are gonna move on through this space. Now, here's the deal. Whenever the electrons are gonna move to the metal piece, they're gonna collide with the stationary ions, and there will be friction. Friction will produce heating. Do you understand?
Yes, sir.
এই পর্যন্ত বুঝা গেছে কিনা যে হিটিং প্রডিউস হবে কেন? আমি আবার
এখন স্যার
এই পার্টটা আবার বলতেছি। As the electrons will be pushed down from towards the lower direction, as the electrons will be pushed down towards the lower direction, they will be leaving from this rectangular region because they will be pushed downwards because of the presence of the magnetic field. And so logically, this place would become void of electrons, but that's not supposed to be maintained because this is a metal piece. There are lots of electrons. So other electrons will essentially rush into this place. So essentially, this would produce a cyclic flow of electrons. In this case, electrons will be coming out through this direction, and they're going to fill it up on this direction. So if this is the direction of the electrons, I can draw that conventional current, which is essentially called the eddy current, will be happening in the opposite direction. So eddy current will be happening like this, and conventional current and electron flow will happen like this. So there'll be a pretty high amount of current produced by a lot of electrons that will exist within the metal piece because of the application of a magnetic field onto this disk. And because all the parts are not affected by the same amount of magnetic field, we have affected only a small part of the disk as a magnetic field. That's why we are going to have this flow of electron essentially moving through the plate itself. All of these electrons, as they move around through the lattice of the metal, because the electrons are physically traveling from the lower side of this rectangular part all the way to the top side of the rectangular part, they are going to collide with the fixed ions of the metal piece. That will develop resistance, and that will give you extreme amount of heating. We are talking about moving millions, if not billions, of electrons. So all the individual electrons will produce some significant amount of heat energy. Now, if you wonder, why does this heat energy is coming from? This heat energy, because energy is indestructible, it cannot be created or produced, can only convert from another form. So this heat energy will essentially be coming from the kinetic energy of the disk. You have to understand this thing. The reason the electrons are having this kind of movement, because the disk was rotating in the first place. If the disk did not rotate, these electrons would not have any reason to move. They could pretty much be stationary within a stationary magnetic field. The only reason the electrons are made to move because of the rotation of the disk and also the simultaneous presence of the magnetic field. So the disk had some kinetic energy to begin with. As the electrons are made to move within the metal disk because of the presence of the magnetic field, they will produce some heating. That heat energy will be directly drawn from the kinetic energy of the wheel, which means if it is a high-speed metal disk and we introduce the magnetic field over here, this disk is going to start to slow down and heat up, which can work as a very well braking system for extremely high-speed vehicles. Because the higher the speed of the disk, or the higher the rotation of the disk is, the faster you can extract energy out of it. Because how much electrons are going to move, or how fast the electrons are going to move, is very much dependent on how fast the disk was rotating. So if the disk is rotating at a very high speed, you can extract energy pretty fast. So it can work as a very efficient braking system for high-speed vehicles. But for low-speed vehicles, it's not going to work that good, because if the disk is rotating at a low speed, essentially you're not going to have that much cutting, you're not going to have that much current. So the rate of energy drawn out, or conversion from kinetic to heat energy, wouldn't be as effective. This current is what we call eddy current, and this eddy current and the braking system that I just tried to discuss is called eddy breaking. It is exclusively, not exclusively, it is more applicable to vehicles which have an extremely high amount of, which move really, really fast. for example, a very common use for eddy braking is used in bullet trains in Japan or other places in the world where they have electric trains, bullet trains, because at extremely high speed, friction brakes don't work very well. There are certain materials, ceramics and other, which can work pretty well, but eddy braking can be very smoothly and controlledly applied at very high speed vehicles to maintain a very uniform deceleration. So, and the beauty of this whole system is that you can have different amount of effectiveness of braking depending upon the speed of the vehicle. For example, if the train is moving really fast, you can apply your disc. I mean, if we apply the disc close to the center, we're gonna have less braking. If we apply the disc farther out on the center, we're gonna have more braking effect. And there is a reason for this. So here in this description, I actually described how the electrons are gonna move, and that's how I went on to describe how the eddy current will be produced. There is another way. This is actually what happens. Physically, this is the scenario. But there is a different way to explain eddy current. It's the same thing, but there is a different way of explaining it. The other way, the alternate way to define eddy current can go on like this, is that, I have this thing over here somewhere. Yeah, and within this booklet, we have a pretty nice figure for eddy current, eddy braking. Exactly, this one. So another way to explain the eddy current, it can work also like that, is that this is let's say this is a circular region of magnetic field that we're applying over here, and these are some radial segments of the whole disk which is being shown. The angular speed is same for all the places. The angular speed is same for all the spaces of this disk, but the linear speed is different. Close to the center, the linear speed is less. As you go farther out, your linear speed is bigger. So whenever you are making the disk to pass through a magnetic field, the amount of cutting that you have over at this region, the speed of cutting that you have over at this region is much smaller. Rate of cutting over here is much smaller compared to the rate of cutting over here. This part, having a much higher speed of movement, linear speed of movement, will cut the magnetic field far too faster. So you're going to essentially produce EMF in both regions because of the cutting, because whenever moving charges cut across field lines, they produce EMF. But you will have a much bigger EMF produced over here in terms of magnitude. You're going to produce a much smaller EMF produced over here, which means you are going to produce a voltage difference across these parts. Now, as you can see over here, they have they have shown the current direction. So if you go through the considering the direction of voltages, this would be the high voltage point because there is more current. There is more cutting. This will be the low voltage point because there is less cutting. So this will work like a battery. Because of the movement, the conventional current, will be pushed out from here, and it is going to try to go through the other part of the metal disc into the low voltage part. So through the external part of the magnetic field, the current is going to try to come back to the top side, and current is going to come out from the bottom side because of the different rate of flux cutting. So that's another way to explain this thing. It's the same thing, but this is just a different way of explaining. So the first explanation was I used the basic concept of electron, that an electron was entering the magnetic field. It experienced some force. The force produced current. That's eddy current. That was the first explanation that I used. The second set of explanation can go on that whenever different part of the same metal body is cutting across the magnetic field at different linear speed, we're going to have different value of voltages on different parts of that metal disc. Naturally, conventional current will flow from the high voltage region to the low voltage region through the other parts of the metal disc which is not affected by that magnetic field. That is eddy current. It's basically the same thing, but explained in two different ways. A explanation to pore dekho shobai. If you have any question, you ask me about it right now. Read these 2 paragraphs, 3 paragraphs. Any question? I'll take questions now. Yes, Avias, go ahead.
Sir, why are the electrons moving like this?
Because they are physically moved across a magnetic field. When electrons are existing on the metal disk, normally, naturally, but the moment they enter into the magnetic field in a moving condition, they are being pushed by that magnetic field by Fleming's left-hand rule.
Yes, sir, I understand that they move radially outward, but why do they circle back into the magnetic field?
Because, well, if they were only being pushed outwards, let's say if they are only being pushed outwards, shouldn't this region become void of electrons?
Yes, sir.
But can we have that? It's a sea of electron out there. So the moment electrons are coming out through the bottom side, other electrons are definitely going to fill that up void.
Other electrons, sir?
Other electrons means the other electrons existing in the metal disk. So it produces a flow of electron, a flush of electrons, or like a flood of electrons into the region from the top and outwards at the bottom.
I understand, sir.
Sure.
Sorry, you're telling that it can come from all directions. Clockwise or anti-clockwise direction take another.
No. It can come in all directions, essentially meaning that all the parts where this magnetic field is working, the electrons are being pushed in one direction. All the other parts where the magnetic field is not working, that's where the return part can be. Because in the part where the magnetic field is affecting the metal disk, within this part, the electrons cannot move upwards. Within this part, the electrons have to move downwards, which means to fill up that void, electrons have to move upwards in some other places where the magnetic field is not working, which means this eddy current mechanical braking system is only applicable if you apply multiple different magnets, but not the entire thing under a single magnet. If we apply the entire thing under a single magnet, the electrons will be pushed within the same side. So for example, if we had a very large magnet, let's say if we had a really large north pole, let's say circle blue, if we had a really large north pole and south pole applying like this, in that scenario we would simply have a very high negative voltage on the periphery and a very high positive voltage at the center, and it would remain at that voltage difference throughout its duration. We would not have any eddy current because the electrons would not have any return path. To achieve eddy current, you need to have certain locations under the magnetic field effect, certain locations free of the magnetic field effect, so that those free locations can work as the return part of the current, which completes the circuit within the metal disk. Does it answer your question?
That's right. I'm still confused. If the entire region is covered by a magnetic field, it can still move from the higher potential to the lower potential. Tendency still move করার.
Yeah, exactly. But the problem is this is going to happen. For example, if this whole thing is under the effect of a very large magnet, an uniform magnet, in that case, all the parts would experience the electrons to be pushed outwards. There would not be any free region of magnetic field where the electrons would be free of the magnetic field's force, so that they can actually come back to the deficient parts, which means this would cause the entire periphery to become highly concentrated of electrons, and the central part would become almost void of electrons. So you'll have a high positive charge, a positive voltage at the center, and you'll have a high negative charge at the center, which can work as sort of like a DC motor, DC supply, but it is not going to work as eddy current. But
just
to have
EMF to build up with
the exactly.
No movement.
But because you don't have any unaffected return path available, electrons cannot produce the eddy current within the metal disk itself. They cannot. To have the eddy current available, you need to have alternate segments of regions which are affected by magnetic field and non-affected regions. You need both of them.
Yes, sir. Buchi.
Beautiful. Shubhro, go ahead.
Sir, can we say that this is comparable to what happens in a convectional current? Like, when স্যার যে আপার ধরেন যে স্যার লিকুইডের মধ্যে যেমন হয় যে একটা হাই পটেনশিয়াল থেকে লো পটেনশিয়ালে যাচ্ছে, ইটস আ বিট লাইক দ্যাট, ইজন্ট ইট?
Yeah, definitely. Yeah, you can compare it to that physical conventional current of heat. Yeah, you can compare it to that. It's not identical, but it's very much comparable.
Yeah.
Yes.
Okay.
Sir, I have a question involving the diagram.
Yes, go ahead.
Can you show the diagram? Sir, what does F mean on the figure B?
This
Why is
F, this
the,
F means the physical force onto the electrons. Does this F has any description over here? No, it doesn't. Okay. Okay, I'll explain this F. Don't worry. This was going in which direction? Clockwise direction, and the force was anti-clockwise. Okay, let's come to this figure. Acha, this is a bit hazy, but bear with me. In this case, the current was happening in upward direction, right? The conventional current was happening. Let me use a darker color in upward direction for this region. Can we agree on that? Electrons are coming down from the bottom. The conventional current is upwards. ठीक है?
yes, sir.
Now, if you use this conventional current, and try to find out the direction of the force that this conventional current will produce onto the disk, what would be the direction of that force? What is the direction of the force that this current will produce onto this disk?
Sir, downward.
No. Aim your index finger into the screen, align your middle finger towards the center, and extend up your thumb. Where does your thumb aim?
Sir, to the left.
To the left. Exactly, to the left. So let me draw that with, let's say, red. So in this case, the force would be available to the left, which means this region will always be applying a leftward force onto the disk itself. The disk was rotating in the anti-clockwise direction. If this force is to the left, then this will be working as an opposing force, hence the braking. So this force over here was representing the braking force that this eddy current is producing out of this region.
So in this case, the magnetic field is into the page.
I have to read it. Current, hold up, force, I'll align the force, current downwards. Yes, into the page, it's still into the page, yeah. Yeah.
If it's into the page, sir, and it's rotating in clockwise, why are the electrons still going down?
No, these are the flow paths for the eddy current. They have not shown the path.
This is not the electrons, it's convection.
Yeah. I do the exact opposite figure because I consider anti-clockwise direction. So that's why my figure is absolutely opposite of this one, but the mechanism essentially is perfectly identical.
I understand, sir, but it's easy to get confused. Could you give this PDF in the group?
Yeah, I mean, essentially, they don't usually ever show the pathway of electrons in figures. The reason I brought about the idea of electrons is to give you the actual microscopic understanding for what is essentially happening. So any figure of eddy current that you are going to come across in any printed material would always have the direction of the eddy current itself, not the electrons. So if you're trying to figure out the direction of the electrons, you have to assume it is opposite to the current of the direction of the eddy currents. They would usually never show you the flow path of the electrons. That's not how things work. Conventional currents or eddy current would be labeled in the figure. I use the direction of the electron to make sense, to give you the concept that why it happens at a microscopic level. Clear?
Yes, sir.
Okay. Same stuff, eddy current can be used for cooking. And that's what we saw over here on the other thing. This is how an eddy current can be used for cooking. Have a look. It's a very simple thing. This is a metal coil. This is a coil which will be fed by an alternating current. And this is just a very basic metal disc. Pretty basic metal disc. What is important is that the size of this coil is small compared to the diameter of this metal disc. This metal disc is not connected to any electrical appliance. This coil is the electrical part, which is kept absolutely electrically insulated from this metal disc. So what is happening? Whenever we'll feed AC voltage into this coil, it will produce a variable magnetic field into this coil. Now, because this is already an AC, the closer parts would be affected by a stronger variation of voltage, magnetic flux variation, magnetic flux, the further part would be affected by a weaker variation of magnetic flux. It means the value of d phi or delta phi. Do you know what is phi? Remember?
Linkage.
The flux linkage. The delta phi would be much stronger for the closer part of the coil. The delta phi would be much weaker for the further part of the coil, which means because of the difference of the delta phi's, there will be difference of EMF generated, and this difference would be maintained as long as the AC will continue. So basically what's going to happen, electrons are going to continuously flow within this disk, radially outwards and radially inwards, radially outwards and radially inwards in the same frequency as the frequency of the AC supply. So do you understand my point?
স্যার আপনি বললেন phi হচ্ছে ম্যাগনেটিক ফ্লাক্স লিংকেজ, তাই তো?
Yes. So
মানে স্যার ডিরেকশন চেঞ্জ হতে থাকে কারেন্টের এখানে।
this coil is fed with AC supply. So the closer part of the metal plate would be affected by a bigger variation of magnetic flux linkage. The radial parts or the distant part of the metal plate would be affected by a smaller variation of the magnetic flux linkage. So there would be higher EMF variation produced. For example, let's say close to the center, the variation of absolute EMF compared to ground 0 volt is, let's say, plus minus 200 volts for maximum and minimum value. Whereas on the periphery, let's say the voltage variation is plus minus 10 volt, which means for most duration of the part, you will always have some voltage difference from the center to the outwards, which means electrons will be continuously be going outwards, towards the border for half the cycle, and for the other half cycle they'll be pushed inward. So electrons will be continuously going back and forth within this metal piece because of the variation of this magnetic field. So this metal plate is not attached to the coil. This is absolutely free of the electricity, but because of the internal flow of the electrons, this metal plate is going to heat up, and that heat can be transferred to the cooking pot, and that can cook all the stuffs. If our cooking pot is also made up of metal, that metal pot itself will be also affected by that current. For example, if this is a metallic pot, this number 2, this is a metallic pot, that base of the metal pot will also be involved within that process. So simultaneously you'll be heating up this plate, you'll be also heating up this your cooking pot's bottom as well. So you'll be having a pretty strong heating where the heating surface is not at all electrically connected, which makes it extremely safe and also pretty efficient cooking mechanism. It is far too efficient compared to basic electrical heating. Electricity going through a resistor producing heating, tar theke ei heating process onek beshi efficient, because we are essentially moving a huge number of electrons, which are pretty much all the electrons which is available within the metal disk. We are affecting all of them. So the amount of current that we're talking about, current is essentially the I equals to Q by T. We are talking about moving a huge number of electrons every second and continuously back and forth. So that you will be producing a huge amount of friction with the lattice ions, and as a result, the heating effect can be pretty intense. That's how induction cookers work, which is basically all the typical cooking stoves that you see on online cooking shows. They connect the electricity pot, and that is not an resistance heater. Those are all induction heater. Yes, Ramisa.
Sir, I'm in a diagram, like it's hard to understand the components. Can you draw it separately and tell me which is what? Because I'm বুঝতে পারছি না.
Okay, I'll help. Sure, no problem. Let's say I'm drawing a top view. Let's say this is the disk of metal disk of cooking pot on which we're going to place the cooking pot. So let's mark this as ash color and fill it up with ash color. Okay. Under this metallic plate, we have a coil. Let's say that coil is this green circle, which is not as big as the disk. That's pretty important. It's a bit smaller, and it essentially has two lines because current is coming out and current is going in. So this is connected to an AC supply. So what I mean is that this is connected to an AC supply of some variable voltage. So whenever the magnetic flux lines are going to come up, they are going to affect the central region more strongly, because here the magnetic field will be very concentrated, compared to the periphery. So the amount of magnitude of delta phi would be very large over here compared to the delta phi's over onto the surface areas. Can you appreciate this much? It's about the variation of the magnetic field flux linkage. It's about the concentration of the magnetic field lines. রামেশা এটা বোঝা যাচ্ছে কিনা?
হ্যাঁ স্যার এটা বুঝছি।
ঠিক আছে। সো এইখানে আমাদের মানে রিভার্সিবল ডিরেকশন অফ কারেন্টের জন্য এখানে আমাদের কিছু ইএমএফ প্রডিউস হবে because the this could be cut by variable magnetic field. Let's assume the absolute voltage that we could possibly get for, let's say, this inner circle. Let's assume এইখানে আমরা পাচ্ছি হচ্ছে about, let's say, plus minus 200 volt. So I'm using plus minus because of the magnetic field current flow direction change. So let's say this is plus minus 200 volt. Let's say on the periphery we're going to get plus minus 10 volt only, which means whenever this is plus 200, the periphery is plus 10. So this is the high voltage region. The entire outer circle is plus 10 volt. So in that case, conventional current will be flowing outwards. Eddy current. In the reverse cycle, the center, let's say, become minus 200 volt, and the periphery becomes minus 10 volt. So in that case, the periphery is the high voltage and the center is the lower voltage. So current in that half cycle, current will be traveling from the radius to the inward. So in all the directions, current will be traveling back and forth like this, going back and forth, মানে concentrating and spreading, concentrating and spreading, concentrating and spreading, like that. That basically produces the heating.
স্যার এটা এসি তেই তার মানে শুধু এসি কারেন্ট দিয়ে করতে হবে তার
এটা শুধুমাত্র এসি কারেন্ট দিয়ে করতে হবে, এটা ডিসি দিয়ে করা যাবে না। রামেশা বুঝা গেছে কি?
Yes sir, I understand.
Beautiful. Any other question? তোমাদের সিলেবাসে এই দুটা ইউজি আছে ইলাবোরেটলি, একটা হচ্ছে ইন্ডাকশন কুকিং আর হচ্ছে এডি কারেন্ট ব্রেকিং। সো এই দুটার উপর বেস করে কোশ্চেন হয়, যদি খুব রেয়ার, বাট দিস আর টাস্কস দ্যাট আই উড লাইক ইউ টু আন্ডারস্ট্যান্ড।
স্যার আগের কেসে যেমন দ্য ইলেকট্রন ওয়াজ মুভিং ইন আ ক্লকওয়াইজ এন্ড অ্যান্টি ক্লকওয়াইজ সার্কেল, এখানে তো এটা হচ্ছে না।
নো আগের কেসে যে জিনিসটা ছিল সেটা হচ্ছে উই ওয়ার অ্যাপ্লাইং আ ফিক্সড ম্যাগনেটিক ফিল্ড, fixed strength of magnetic field. For example, if it's this magnetic field was introduced by some permanent magnet, or this field was magnetic field was introduced by some by a DC solenoid of fixed current value, and the disk was rotating, that was producing the eddy current because different segments of the metal piece were affected by different value of magnetic flux linkage. Some places where there were magnetic flux linkage, some places there were no magnetic flux linkage. And that was the case for that one. So the variation over here was produced by the physical movement of the disk. The variation in this case is being produced by the variability of the supply, or the magnetic flux itself is the variable over here. The disk is not moving at all. বুঝা গেছে?
জি স্যার।
Beautiful. So that's that. এখানে আরো দুটো এক্সাম্পল আছে, metal detectors and electrical guitars, এগুলো তোমাদের সিলেবাসে হাইলাইট করা নাই, so I'm not going to go through this, but you're going to essentially have this booklet, so you can read it through. If you're interested, you can look up some other internet stuffs to make it more clear to you. Do you have anything else to cover from here? We talked about the diode thing, we did discuss them. We talked about the stuffs. This is the velocity selection figure, we also talked about this as well. No, there is not much. I'll share up the PDFs for the notes and also the worksheets as well in PDF form, which will be essentially printed and eventually made available to you after I have done with the P5 compilation preparation. I have already printed some 40 booklets and about, I think, 8 mark schemes, and more underway.
স্যার আমরা কি P4 এর জন্য আবার বুকলেট?
হ্যাঁ, P4 এর জন্য তোমরা কতটুকু পর্যন্ত পাইছো? তো P4 এর বুকলেট তোমরা পাইছো ক্যাপাসিটর পর্যন্ত। ক্যাপাসিটরের পরে তো আরো টপিক পড়াইছি, ক্যাপাসিটরের ইমিডিয়েট পরে তো আমরা ইলেকট্রোম্যাগনেটিজম শুরু করলাম। So you're gonna get another booklet on electromagnetism, photoelectric effect, and arta topic আছে,
কোয়ান্টাম ফিজিক্স।
photoelectric effect হচ্ছে কোয়ান্টাম ফিজিক্স। So ওই photoelectric effect, আরটা হচ্ছে এটার নাম কি, রেডিওঅ্যাক্টিভিটি। এই তিনটা মিলে তোমরা আরেকটা বুকলেট পাবা, এবং একদম সিলেবাসে যে লাস্ট যে সেগমেন্টটা আছে অ্যাপ্লিকেশন বুকলেট, ওটার উপর আরেকটা ইন্ডিভিজুয়াল বুকলেট পাবা।
স্যার আমাদের কি রেডিওঅ্যাক্টিভিটি এটাতে আছে?
ডেফিনেটলি, এবং আরো অনেক ইলাবোরেটলি আছে, অনেক ক্যালকুলেশন করতে হবে। And radioactivity calculations are the calculations where you have to do your calculations up to 5 or 6 decimal places, because that variation of mass can give rise to enormous amount of energy. Those are the only maths where you have to go for an extremely high decimal place of calculation. Other than that, your answer is not going to make sense. It's interesting. I'll try to make it interesting for you. Okay.
Sir,
Yes.
do we have anything that any questions that relate eddy currents to damping?
Yeah. Definitely. Beautiful pick off. I'll definitely show you this on the SHMA. This is a simple harmonic motion worksheet where we actually left off some questions due to the eddy current stuff, and I told you that this will be more understandable when you have discussed eddy current. So let's pick up at least one or two of them.
উপরে মনে একটা ছিল
ছিল
noticed a magnet.
Where? Play-Doh. Oh, got it. Number 2, an aluminum sheet is suspended from an oscillator by means of a spring, as illustrated in figure 3.1. An electromagnet is placed a short distance from the center of the aluminum sheet. So this is what is happening. In this case, without the presence of the electromagnet, if we give this aluminum sheet a bit of a vibration, it's going to vibrate for a pretty long time. Because in that case, it will be underdamped only by the air resistance. Aluminum sheet, high inertia, and so it's going to lose energy pretty weakly. So it's going to be able to maintain its vibration for a very long time. But let's say if you turn on the electromagnet and then give it a bit of a vibration, then the energy will be dissipated out really fast. Let me tell you why. This is the DC solenoid, and here, as the aluminum sheet will be moving, this thing is very much similar as the rotating disc. When the aluminum sheet is going down, those electrons are going to produce the current within. So there will be eddy current produced in the aluminum sheet as long as it is at some movement with respect to the electromagnet. So each of those motions, downwards or upwards, we will be having eddy currents in opposite directions, which is going to slowly eat up the kinetic energy of the aluminum sheet and convert that into heat energy. So that way, we're going to have much stronger damping effect, or the vibration will die out much earlier. This is the effect of those electromagnetic thing. বুঝা গেছে কিনা দেখো?
Sir, the current in the aluminum sheet, the eddy currents are also alternating in direction, right?
Definitely. In this case, yes. Definitely. I mean, the direction of current that you're going to have as the aluminum sheet is going down is going to be in one way, and as the aluminum sheet is going up, it will be in a different way because it is going up and down. For the circular disc figure, the metal part was always entering the magnetic field from left to right, from the figure that I drew. So the metal part is entering the metal disc always from left to right. This was a uniform direction, but this is not true for the aluminum sheet because it is going up and down. So for half the oscillation, the metal part will be entering from top to down. For the other half oscillation, it will be going from down to top. So you're going to have reverse of entering direction for the metal part that would essentially reverse the eddy current direction as well. Definitely, yes.
মানে স্যার অসিলেশনের জন্য বেসিক্যালি ডিরেকশন এখানে চেঞ্জ হচ্ছে।
Yep.
আর স্যার হিটেড আপ হয়ে যাবে না তাহলে অ্যালুমিনিয়াম শীটটা যদি মানে সাফিশিয়েন্ট অ্যামাউন্ট অফ কারেন্ট
it will be definitely heated up. That amount of heat energy might not be deadly for us to touch it, but it would make significant decrease, visible decrease on the oscillation amplitude. You can essentially touch the device, touch the aluminum piece. You might feel it a bit hot, but it is not supposed to become red hot or glowing hot or burning hot. To achieve that, we would have to do we would have to have a very strong magnetic field with a really large amount of amplitude of motion. I mean, to maintain that amount of heat. Plus, it's a metal piece which is suspended in air, so you can always lose heat by convection. That is a given.
বাট স্যার ফ্রিকশনটা এখানে যা হচ্ছে ইলেকট্রনের কারণে ওইগুলো আসলে হচ্ছে ড্যাম্পিং ইফেক্ট দিচ্ছে।
Yes, essentially. That internal movement of those electrons is heating up the coil, which is coming from the kinetic energy of the movement. I mean, or in other words, you can say that in the very way I explained the force thing a bit later when Abias asked the question that what was that F about? I mean, because of the eddy current or because of the electromagnetic being present, whenever the aluminum sheet is going to try to go downwards, eddy current is going to produce an opposing force. Eddy current will produce an upward force. When that
Okay.
emission is going to go upwards, eddy current is going to produce a downward force. So eddy current will always oppose the direction of the movement. Hence, you will have a bigger damping. That is also another way of explanation, which perfectly works. So this is another question that we have. Similar stuff. We have a helical spring. We have a magnet. We have a coil. I think this is not one of this question. This is here we are actually still producing voltage by vibration. Oh, আচ্ছা এই কোশ্চেন পুরোটাই হচ্ছে মনে হয় ইলেক্ট্রোম্যাগনেটিজমের উপর। লাস্টে শুধু গ্রাফ একটা আছে, এই পার্টটুকু পুরোটা ইলেক্ট্রোম্যাগনেটিজমের উপর। This is something that you should be able to answer. Let's give it a try. See if we can answer this question. So we have a helical spring, magnet, coil, voltmeter. The magnet is displaced vertically and then released. We have the voltage being produced, apparently uniform. Good. State Faraday's law of electromagnetic induction. So what is Faraday's law of electromagnetic induction?
So induced EMF is proportional to
Rate of change of magnetic flux.
rate of change of
Beautiful.
magnetic flux.
Exactly. Induced EMF is directly proportional to the rate of change of magnetic flux. So number 2, the will say use Faraday's law to explain why there is reading on the voltmeter. You'll explain this. The reading varies in magnitude. The reading has both positive and negative values. So এগুলা ভাষার সাথে গুছায় লিখবা। এরপর বলছে use figure 5.2 to determine the frequency of the oscillation. আচ্ছা এই পরের কোশ্চেনগুলো অ্যাকচুয়ালি ডাম্প, এগুলা বলে লাভ নাই। Let's see if we have anything else that is relevant for that eddy current thingy. Maybe there isn't. No, there is one. This is the another one. So this is what happened. This is what is happening over here. So they started the magnet to oscillate without the switch open. I mean, keeping the switch open. So so initially the coil was not present, physically not present, because the circuit was open. So for this much duration, or I can say about this much duration, the switch was open. So there was no significant damping force. You have the same amplitude. At this instant, they close the switch. So now you have a gradual drop, significant visual drop of the amplitude. So that's the damping effect. So let's have a look at this question. A bar magnet is suspended from the free end of a helical spring, as illustrated in figure 3.1. One pole of the magnet is situated in a coil of wire. The coil is connected in series with a switch and a resistor. The switch is open. The magnet is displaced vertically and then released. As the magnet passes through its rest position, a timer is started. The variation with time t of the vertical distance y of the magnet from its rest position is shown in figure 3.2. Okay. At time t goes to 4.0, the switch is closed. Okay. So this is where they close the switch. Beautiful. Makes sense. Use figure 3.2 to determine state with the reason whether the damping after the time is light, critical, or heavy. It is definitely light damping. If it was critical damping, it would directly come to 0. If it was heavy damping, then we would not see it. Would also come to almost 0, but it would not reach the equilibrium. But the the vibration would essentially stop. So it is state with a reason. So it is a light damping because the oscillation is still continuing, but losing in a gradual decrement. I think that's the correct answer.
Should we say it decreases exponentially?
Can you derive it from the graph? It decreases exponentially. You can say that also. I mean, it decreases, but the amount of decrease decreases over time. That's basically exponential. Yeah, that's just the word version of decreases exponentially.
So this damping is due to eddy current still?
That's the reason. But the question says, by observing from the figure, what evidence of that graph tells you that what type of damping is there? You said the physical reason why the damping is happening. But the question is about detection of that type of damping from the given graph. So, no. What you said is correct for the scenario, but that is not what was asked. Buchabias.
Yes, sir. I was just confused.
No, it's okay. No big deal. Number 30. Let's have a look. amplitude decreases gradually, light damage. So they only use the term gradually. How about the example? So the amplitude decreases gradually and therefore the damping is light. A statement to the effect that either the amplitude decreases during a few periods or that the amplitude decreases exponentially is not adequate to distinguish between different forms of damping. What? A statement to the effect that either the amplitude decreases during a few periods or that the amplitude decreases exponentially is not adequate to distinguish between different forms of damping. What does that mean? Anyway, I would write the answer in this format. The oscillation continues. So it is not critical damping, neither heavy damping. Because what happens in critical damping, the oscillation stops and the object comes back to the equilibrium positions immediately. What happens in heavy damping, the oscillation stops, the object does not come to the equilibrium position, stays a bit above, but the oscillation stops immediately. That's the first thing for critical or heavy damping. And in light damping, the oscillation keeps continued, but it slowly or gradually loses the amplitude. So I would first define that this is not critical or heavy because the oscillation continues. That's why it is not light, heavy damping or critical damping. As the amplitude of the oscillation decreases gradually, it is light damping. I would definitely go in that type of wording. I would usually not go for exponentially. I have a reason for this. We can see that the decrease is decreasing, but whether it is actually exponential, doesn't that require a bit of mathematical calculation to determine whether a decreasing pattern is exponential or not? All the math people, please respond. R minus এখানে? Do we have Armine here?
No, sir.
Nai?
No, sir.
Okay. Okay. I think some calculation, mathematical calculation or proofing is required to define a relationship is exponential. I think so, but I'm not very sure about it. I would
So
not,
আমরা যদি peak গুলা join করে দিই, like the shape is almost exponential, right? Like এর আগেও তো Marx scheme ছিল almost.
but the thing that is they're saying that exclusively saying that the relation, the decrease is exponential is not good enough to ascertain that this is to distinguish between the different type of damping would essentially mean that if you only write that term, you are not gonna be credited for that mark.
তাহলে কি gradual decrease বলা, I guess তাহলে better.
এটা খাচ্ছি রাখো। হ্যাঁ, গ্র্যাজুয়াল ডিক্রিজ বলে মানে ভালো হবে। এটা ফ্রিজে রাখো, এটা এখন খাবো না, নষ্ট হবে, দিনে খাবো কাল। অথবা শোনো, আম্মাকে দেখাও, আম্মা রাতে রুটি খেতে পারেন, আম্মাকে দেখাও, আম্মা খাবেন কেন? হ্যাঁ, গ্র্যাজুয়াল ডিক্রিজ লিখে আমার মনে হয় বেটার হয়। That would be a, I mean the examination report is pretty trippy, if you ask me. It's just weird. Determine the natural frequency of the vibration of the magnet on the spring. That's possible. The state Faraday's law of electromagnetic induction. We just discussed that. Explain why after time t equals to 4 the amplitude of the vibration of the magnet is seen to decrease. Achha, this is exactly where the eddy current thing will come in. So here you can use the term eddy current, and this is a 4-mark question, which should make it pretty interesting. Kids, think about it. How would you answer this? Explain why after time t equals to 4.0 the amplitude of vibration of the magnet is seen to decrease. Why? You can, I think we can use Lenz's law and with eddy current, both of them. I mean, I could say that when the switch is closed, as the magnet moves up and down, according to Lenz's law, the coil produces an opposing force on the magnet's movement, which increases the damping. And
Or can we say the magnet cuts across the coil, so it produces electric current, and this energy comes from the kinetic energy of the magnet, hence it slows down.
I wouldn't be so sure about that. You see, for eddy current to be in existence, one of the important bit for eddy current to be in existence is that we need to have a pre-existing magnetic field, either from an AC supply or from a DC supply. Here we do not have any magnetic field other than the magnet itself. So I don't think using the term eddy current in this case would be a very good idea. I think the Lenz's law in this case is more appropriate. Think about it. Eddy current is দুটো example আমরা আলাপ করলাম। একটাতে in one of the examples we had a rotating disk which was affected by a fixed magnetic field, and then in the second example we had a fixed disk which was affected by an alternating magnetic field. So you had a pre-created, pre-existing magnetic field in action for the eddy current to be relevant. But that is not the case over here because we do not have essentially a solenoid produced out of this coil. Well, this is a solenoid, but it does not have any physical energy source, neither a DC solenoid or nor an AC solenoid. You cannot say that. All that it is working is to oppose the motion of the magnet following Lenz's law. I think in this case, Lenz's law would be more relevant compared to eddy current. I would not go for eddy current now that I think about it. Let's have a look at the Mark scheme. But Rafi, did you get my reason?
Yes, sir.
A current is introduced in the coil. As magnet moves in the coil, current in resistor gives rise to a heating effect. Oh, they have gone for the heating effect. Thermal energy is derived from the energy of the oscillation of the magnet. Wow. No mention of Lenz's law whatsoever. Many answers indicated a lack of ability of to apply concepts to various situations. So crucially, candidates failed to state where the current would be induced. Many were content to invoke Lenz's law without making it clear that the induced can give rise to heating effect in the resistance, and that this thermal energy is derived from the energy of oscillation of the magnet. Okay, I fell for that trap.
Exact opposite of your expectations.
Sir.
So they didn't use the term eddy current over here, but they essentially went out for the energy transfer, which I can make sense with. Hey, bolo, Ramisa bolo.
Sir, Lenz's law does seem more appropriate in this case because মানে এরকমই একটা situation তো Lenz's law তে আমরা পড়েছি, so like that is the first thing that comes to my mind. How am I supposed to think? And like you just gave an explanation as to why eddy current shouldn't work, and I had ওভাবেই আমি চিন্তা করতেছিলাম. So what is the change now?
Here's what I believe. What they have written over in the exam, so have a look. Crucially, candidates fail to state where the current would be induced. Okay, we can always say the current would be induced in the coil. That is a given. Many were content to invoke Lenz's law without making it clear that the induced current gives rise to a heating effect in the resistance, and that this thermal energy is derived from the energy of oscillation from the magnet. So here's the trouble. Why the question was, what was the question? Let's look at the question again. Explain why after time t equals to 4.0, the amplitude of the vibration of the magnet is seen to decrease. Now here's the deal. The amplitude decrease of the magnet can be explained in terms of energy transfer, which they did. That can be easily done by, that can be easily also explained equally acceptably by the presence of an opposing force. Because we are talking about how the vibration amplitude was decreased. Amplitude decrease does not exclusively have to be relevant to energy transfer. It can be also be explained in terms of opposing force being present within the setup. So if we invoke Lenz's law and talk about the existence of opposite forces because of the solenoid producing opposite poles of the magnet, and it is doing attraction and repulsion, if we go for that elaborate discussion, that should make a good answer. For reasons unknown, they exclusively lined for the energy transfer idea. I don't know why that is, but using the idea of forces should also be a perfectly okay way to answer this question. That's just my opinion. But CIE would never enter into discussion about any of the mark schemes, so I cannot ever tell you whether they will agree with me or not. This question can be answered in two different ways. That's just my opinion. You can go for the energy transfer idea, which they did, or you can go for the force involved in the scenario because of the movement and the presence of the closed circuit coil.
And sir, is Lenz's law also related to the energy transfer idea? Because examiners reported some candidates invoked the idea of Lenz's law without talking about heat transfer. Like, ওই দুইটা তো related না. Lenz's law talks about force, or heat transfer to eddy current. So ওটা দুইটা related কিভাবে?
So what exactly is my point? What they are saying that some people only mention the Lenz's law and expected the mark, but what they are expecting that people should say about the Lenz's law and then go for the current existing in the coil, which producing the heating effect, that energy being transferred from the kinetic energy of the magnet, and that's the way that they wanted the answer to be produced by the students. What I'm trying to tell you is that if you even invoke Lenz's law, and if you don't even talk about energy transfer, but only being about the basic content of the Lenz's law, where that the Lenz law tells us what, that any EM induction would be always done in a way that will oppose the region of EM induction, which means whenever the magnet is trying to enter the coil will push the magnet upwards, and when the magnet is trying to go up into the coil, inside the coil will try to pull down the magnet. So if you talk about the forces involved coming in from the Lenz's law and use that idea to induce the damping effect and hence the outcome of reduced amplitude of the oscillation, this should perfectly work out. Valid reasons, proper scientific background, and good structure of point to point, but they did not at all go for that method. That's my point. I mean, using the idea of force, this answer could be also perfectly answered, because they did not essentially tell over here that we have to include the idea of energy transfer. If they did, then I would definitely say that, okay, for using the idea of force wouldn't be good. But they simply asked a very simple question: why the amplitude is seen to be decreased? So you could answer this in terms of energy transfer, or you could also answer this in terms of force. Both of these answers should be equally acceptable. But only mentioning Lenz's law shouldn't be good enough. You have to use Lenz's law in the proper context with proper explanation to make it relevant. I mean, stating Lenz's law and expecting the mark wouldn't be good enough. That goes without saying. But I think I made my point.
Yes, sir, I get it.
Sir,
Yes.
in energy transfer, and when we talk about Lenz's law, is that the work being done against the coil, like when you push the magnet in, you're doing work against the repulsive force, and when you pull it out, do work against the attractive force.
Yes.
That doing that work against that system produces the current in the coil. So why do we need to talk about heating specifically rather than the current being produced in the coil?
That's exactly what I emphasized on my badgering a bit earlier, that exclusive mention of the heating effect should not be a exclusive mark scoring point for this question, because this question can be answered in a lot of different angles. They didn't specify which angle you should aim for. They only asked generally that why is it seen to decrease? So you should have your other options available as well. But if you ask me that if you do write in Lenz's law and bring about the idea of forces and direction of movement and you give it all through description properly, would the examiner still give you mark? Well, in that case, whether the examiner should give you mark or not depends upon their discussion and on their team leader. Because if they did, if any of the examiners prefer to give marks on a proper discussion based upon the force involved from Lenz's law in this question, as far as I understand, CIE would have included that option in the mark schemes as well. So far as I understand, either that was not accepted from the teachers, or no teacher actually was interested to badger the mark scheme with their team leader that this should also be answered, that this was not incorporated in the mark scheme. But this should have been in the mark scheme by all means, if you ask me. Oh, tough world. Learn. What can I say? আচ্ছা, আজকে আর কি করা যায়? Should I start photolytic effect? I can start photolytic effect.
হ্যাঁ স্যার করতে পারেন, শুরু করে দিন।
আধা ঘন্টার মধ্যে
Photolytic effect is very simple.
যতটুকু পারেন।
Acha, I actually need to figure out something. What I understand, maybe some of the people had set out some classes which currently contradict with my routine. That's why I'm having a variability of participants over here. For example, for today's class, the participant number did not even surpass 45. But my last two classes, it was last class it was around 60. So did someone leave permanently? Because depending upon how many people are still with me, I'm gonna print out the booklet number. So I would discuss this in the group chat. Don't worry. Later. So photolytic effect. What do we have in photolytic effect? Let's pull out the big knots. आंखों में मस्ती आय हाय
স্যার
বলো
স্যার আমাদের এই যে টপিক এক্সাম কি
হবে না
হ্যাঁ স্যার এই
জানুয়ারিতে হবে জানুয়ারিতে
স্যার
এক
এটা
মাস
কি
হবে বলো
হ্যাঁ স্যার না স্যার আপনি বলুন
জানুয়ারিতে এক মাস হবে টপিক্যাল মক তারপর হচ্ছে ফেব্রুয়ারি মার্চ এপ্রিল 3 মাস তোমরা ফুল সিলেবাস মক দিবা
স্যার এটা কি মানে বাসায় বসে দিব
হ্যাঁ বাসায় বসেই দিবা সেটা অ্যারেঞ্জ করা হবে তোমাদের জন্য Okay, got it. Mm-hmm. Mm-hmm. Okay.
আচ্ছা স্যার
Yes.
I don't remember Kano, but I missed the first two classes or first few classes of electromagnetism যখন আপনি আগের ক্লাস নিয়েছিলেন ওটার রেকর্ডিং থাকলে কি ওটা একটু আপলোড করে দিতে পারবেন
Yeah, I have one unuploaded lecture for electromagnetism class. Yeah, I will upload them today with date.
Okay, thank you sir.
Sure.
স্যার ওই যে P5 স্টার্ট করার আগেই দিচ্ছি
হ্যাঁ Okay. Let's start to talk about photolytic effect or the quantum physics a little bit. The idea is that Max Planck was a very genius scientist. The way, I mean, what is light? This question has perplexed human minds for a very long time. The first person who actually had recorded documentation to have any idea or theory about light was Isaac Newton. He mentioned, without any physical proof, without any experiment, he thought, and because he was such a genius person, his thought was considered as rule for a very long time. It was not questioned. That what he said is that lights are particle. Any illuminated object sends out small particles from that to our eyes, and those particles vary in size and shape, which gives us the sensation of different colors. That was his theory, based upon no physical evidence, no experimentation. That's what he thought, and it was taken for granted for a pretty long time. Soon, not soon, quite long after, scientists came more interested about waves, and they were doing experiments about reflection, refraction, and sound and other parts. And what they found out that light behaves a lot like waves. For example, the law of reflection, the law of refraction, Snell's law, these laws, and diffraction, the spreading out of light through a hole, these laws perfectly work with light. So at that point, it was decided that light is a wave. But the problem is that the scientists only knew about physical or mechanical waves back then, not physical, mechanical waves back then. So we had ideas about that wave can only exist through a physical medium. Without the presence of a medium, waves cannot exist, because the idea of electromagnetism was not developed till then. So to explain how light could still be a wave, because it can travel through the empty space of the empty vacuum of the space, or it can travel from atom to atom from the in-between spaces. So they came up with an vague term called ether, and they said that ether is an omnipresent medium which is so light that we cannot detect its presence, but it is present everywhere in the universe, even inside the atoms. But it is really, really low density because, but ether is present because lights have to travel through ether. So ether was named as the mythological omnipresent medium through which light waves should be traveling.
স্যার এটা কি বলে টেসলা প্রথম ইয়ে করছিল?
না,
টেসলা করছিল না স্যার? টেসলা তো ইথারের অনেক বড় সাপোর্টার ছিল।
he was not the person who coined the term. It was coined much earlier. I'm not sure if Tesla was a supporter for ether, but he was not the person who coined this term. I think it was Huygens, Homer or Huygens, any of those two people. I'm not essentially sure who it was, but I'm talking about in chronological order. Later, after that, the scientific researchers moved towards electricity, and then there was magnetism. So then what the people did find out that light is actually created from the vibration of charged particles. So it is not, light was defined as an electromagnetic wave. It was still a wave, but it was an electromagnetic wave, which was a new proposition. And electromagnetic waves were defined to be such waves who do not require any physical medium to travel because they are made up from the variation of electric fields and magnetic fields. And electric fields and magnetic fields do not require physical medium for their existence. I mean, in empty space of vacuum, electric field can work. So at that point, light was defined as an electromagnetic wave. Days gone by, scientific researchers went forward, and then sometimes later, someone discovered photoelectric effect. I'm not sure who was the scientist who discovered it, but some scientists discovered photoelectric effect. The idea of photoelectric effect was very stunning and disturbing at the same time. The incident was something like this, that if we have a metal plate and we shoot some very specific characteristic of light onto this metal plate, electrons were seemingly coming out of that plate. And the problem, this was not a big problem, but later scientists did some experiments, I mean rigorous experiments on the photoelectric effect, and those experiments gave us some results which were very, very disturbing. I'll tell you why they were disturbing. The photoelectric effect, experiments of photoelectric effect can be actually summarized, the outcomes can be summarized in a couple of different parts. I'll go one by one. The first interesting part that the scientists found out is that for a specific metal at which light property should there be a photoelectric effect, the variable that would determine whether a metal would give photoelectric effect for a specific light or not, the property which controlled that yes or no was not intensity, it was frequency. A specific metal would give photoelectric effect for a specific frequency of light or above. So there was a minimum frequency value of light for which a specific metal would give out photoelectric effect. Any frequency above, photoelectric effect would still happen, but any frequency below, photoelectric effect would simply not happen, no matter what is the intensity. Now, I need you to understand the difference between frequency and intensity. Intensity is a term that is given by power by area. So it is basically a term that you can think about how many light sources are shining onto a metal piece. For example, let's say if you have a metal piece and you place a light source, let's say 30 centimeter above that metal piece, let's assume if the intensity on that metal piece is, let's say, x watt per meter square, if you bring an identical bulb and place exactly 30 centimeter away from that surface, you would get 2x watt per meter square. If you place a third one, you will get 3x. So the more number of bulbs you'll introduce in identical conditions, you will get more intensity because you'll be supplying more energy per second on per meter square of that area of that metal piece, which means increased number of source can essentially increase the intensity. But the first observation, disturbing observation, was that photolytic effect was the happening of photolytic effect was primarily controlled by frequency. Beneath a certain frequency, photolytic effect would not happen at all, no matter how much intensity you provide. For example, let's say the required frequency of light for a certain metal's photolytic effect is, let's say, 100 hertz. So if we set up a bulb of 100 hertz, we would have photolytic effect. If we set up a bulb of 110 hertz, we'll have photolytic effect. Beautiful. If we set up a bulb of 99 hertz, photolytic effect would not happen. If we set up hundreds of these 99 hertz bulbs, the metal piece would heat up a lot, but photoelectric effect would not happen. This is the first thing you have to take in your head. However, beyond the threshold frequency, this lowest frequency value was named threshold frequency. Threshold means start. Above the threshold frequency, or beyond the threshold frequency value, the photoelectric current means the current that we can capture up from the photoelectric effect by accumulating all the electrons. So photo means light, electron means electron. So photoelectrons means electrons which are produced from light. Photoelectric effect means electrons coming out because of light. Photocurrent means current produced by photoelectrons. So everything relevant to that. What was found out that above the threshold frequency, the intensity of the source is directly proportional to the photocurrent. Photocurrent would mean essentially number of electrons per second. Or what I mean is that, let's say the metal piece that we were talking about, which has a threshold frequency of, let's say, 100 hertz, if you set up a certain source of 100 hertz at certain intensity, let's say in that intensity the photocurrent from that metal piece is, let's say, 2 ampere, let's assume. If you set up an identical bulb of 100 hertz at the same distance, so that you double the intensity, in place of 2 ampere we're going to get 4 ampere. So above the threshold frequency, intensity and photocurrent were directly proportional, but below the threshold frequency, intensity would not be able to even start photoelectric effect.
So like after it meets the minimum frequency, it is being enabled. The photoelectric current is basically being enabled, right? Until then, that's why the intensity is not working, maybe. You can say like that or not.
What you said is correct, but I am not still covering the reasons for it. I'm just telling you what was found. I'll go for the reasons after a while. But I appreciate your input.
Sorry, kind of frequency is like the light turning off and on.
Frequency is like the, it is like, what can I say? It is like the spark of a diesel engine. Like you can have a lot of diesel, but without a spark plug, you cannot turn on a diesel engine. Unlike petrol engine can have auto ignition. You compress the petrol and the air gas certain pressure, it will automatically ignite. But diesel would not ignite. You would need a spark to do that. For photolytic, the frequency is sort of like the presence of the spark plug for the photolytic effect. Sort of. It's not a very good analogy, but somewhat.
That's right. I was asking you, like, by frequency, what do we mean here? When is the frequency taki our power source thakbe oitar frequency?
Yeah. The external light source frequency. The frequency of the light source by which you are shining onto the metal piece.
Sir, je apni threshold frequency ki bollen eta
Threshold, yes.
Sir, ota bujhlam ki.
The minimum frequency for a specific metal at which it starts to give photoelectrons or photoelectric effect. The minimum frequency at which the photoelectric effect starts for a metal is the threshold frequency. It was named the threshold frequency for that metal. For different metal, it can have different values, but the minimum frequency at which the photoelectric effect can happen is the threshold frequency of that metal.
Sir?
Yes?
You're saying the emission of electrons is dependent on how fast I turn off and on the light? Or is it the frequency of the light source? related to the wavelength?
It is frequency of the light wave. It is not frequency of the light source turning on and off. Frequency of the light wave and frequency of the switch being turned on and off are different stuffs. Frequency of a light wave is based upon how fast the charged particle from which that electromagnetic wave was emitted was moving around. Because EM waves, light, any electromagnetic wave is produced by the vibration of a charged particle. So we are talking about the frequency of that source, which ultimately is the frequency of the electromagnetic wave emitted from that source.
Yes, sir.
It might be continuously turned on, but that would cause the vibration in some charged particle within that object, within that source. And that vibration, the frequency of that vibration is what we're talking about here. Okay. So this was the first observation. I'll summarize the observation one more time. It was found that under the threshold frequency, no photolytic effect would happen, no matter how much intensity is provided. However, above the threshold frequency, intensity of the source was found directly proportional to the photocurrent. Observation 1. I'll tell you why this observation was difficult and why this is problematic. But remember this observation. Number 1.
আরেকবার বলেন তো।
তুমি লিখতেছো?
না স্যার, মানে কেটে গেছে।
Under the threshold frequency, intensity had no effect on the photolytic effect, and photolytic effect would not start. Above the threshold frequency, intensity and photocurrent were directly proportional. This is the first observation. Second observation is that observationগুলো ভুলে গেছি, দাঁড়াও, এটা দেখা লাগবে, নোটসে দেখা লাগবে। Okay, I cannot find it in this banner, so let's try a different thing. View extra large icons, maximize the page size, try to find out some photolytic effect stuff. Equals to HF, equals to HF. What is this? Electric field, resonance. Oh, hey, sorry, মনে পড়ছে। The second observation was that photolytic effect was an instantaneous happening. What it means, if light of frequency above threshold frequency, I mean, which can actually produce photolytic effect, is shined upon a piece of metal, the time delay between light falling onto the metal piece and electron coming out was 0. There was no time delay between the metal receiving the light and electron coming out if photolytic effect happens. This was a very disturbing observation as well at that time for the scientists. Now let me explain why the why was photolytic effect so disturbing. These observations were disturbing. Wave theory of light, basic electromagnetic theory as well, wave theory of light gives us the idea that energy transfer from point A to point B happens in a continuous form, like a pipe of water. There is no gap in between. Or let's say if you turn up the tap of your basin, if the stream of water does not break before it drops onto the basin, the type of flow that you have is a continuous stream of water. That's the type of energy flow that happens through the wave. That's the type of energy transfer that happens according to the wave theory of light through the waves. Max Planck, who is a scientist, he proposed that through some of his observation, that he proposed that light rays are not actually continuous. The energy transfer of light happens like in quantum. Quantum means small pieces or small packets. In plural, it's called quanta. And he named all the small light energy particles as photon. So what he said that energy output from energy output from a light source is broken, or it is discrete, or it is discontinuous. So one of the physical ways you can visualize is that the way a shower produces the water flow. Shower never produces stream of water, it produces drops of water. So you can think that this is also a type of water transfer, or let's say energy transfer way, but it's like that. It's like a shower of small energy particles where there is actual physical gap from one particle to another gap. It's not like a string, it's not like a lace, it's not like a continuous thing. There are gaps of thing. Like let's say for example, if you are trying to kill someone with a laser ray, you're gonna beam the laser continuously. Laser, using the term of laser is wrong. How can I use it? So never mind. It's something like bullets. I was trying to get that idea that each bullet is different. So if it's coming out of a gun, they are like individual pieces that's coming out. So that's what Max Planck proposed, that energy from a light source or from an electromagnetic source, they come out in pieces or quantas, in quantums, in small pieces. And he named each of these energy packet as photon. And he came up with the equation that the energy of each of these photon, I'm question to wait karo. The energy of each of these photon was given by the equation E equals to hf. F is the frequency of the source, h is Planck's constant, which is extremely small. The value of h goes by 6.63 into 10 to the power minus 34 joule second. It's very small. Somehow he measured this, or someone else measured this, I'm not sure. But that's the value of Planck's constant. So this is the energy of one photon. So energy of one photon was given by E equals to hf. So he said, if we have a monochromatic light source, single frequency light source, it's gonna give out energy in photons, but each of those photons will have how much energy is directly dependent on the frequency of that source. So if we have a high frequency source, each of those individual photon would be more energetic, or they're gonna have bigger energy. And if we have a low frequency source, they're gonna have low energy amount. Individual photon will have low energy. The problem that we actually came across by the observation of the photoelectric experiment is that wave theory predicts that energy is supplied from one point to another point in a continuous stream. The way wave theory would predict the photoelectric effect goes like this. Energy from any source would flow into the electron. Any electron would absorb that energy over a duration of time, important term, over a duration of time. And whenever the electron would have accumulated enough energy so that it can free itself from the attraction of the electron, because you kids have learned about ionization energy, right? First ionization energy, second ionization energy in chemistry.
Yes, sir.
Yes, sir.
This is about every electron of any object, no matter what type of object you're talking about, they are attached to their atom by some amount of energy. If you want to separate an electron from an atom, you have to feed it some energy so that it can overpower the attraction of the atom and become free of that atom. That's basically how we can make ionization. So if we have to make an ionization, an electron needs to have some energy. The idea of wave theory is that let's assume that in a certain atom, the outer shell layer electron requires, let's say, 10 joule of energy for it to come out of the atom. Its requirement to become free, to be liberated from the atom, is 10 joule. So this amount of energy is what you've learned in your chemistry as first ionization energy, and this is what we call in our quantum physics work function. That's the term, work function. Work function is the minimum amount of energy by which a surface electron can come out after overcoming the attraction of the electron. The term is work function. So I'll be using this term a lot. So if the work function of a certain electron is, let's say, 10 joule, it means to make it free, you need to feed it 10 joule. If it can somehow accumulate 10 joule, it's going to jump out of the electron and become free of it. So free of the attraction of the atom. If we cannot feed the electron 10 joule, let's say if we feed the electron 9 joule of energy, what actually happens, the electron will jump to a higher shell. Now here's the deal. You should understand that the shells that we have defined in our chemistry, these are no physical position. These are some specific energy boundary level. I mean, a shell is not like a flat or not like a surface on which the electrons are moving around. These are like very specific distances from the atom in which the electrons are allowed to exist. So the shell is actually not the name of a thing. It is the name of an orientation. Do you kids understand that?
Yes, sir.
Yes, sir.
You might have read hybridization, like sp to sp3 hybridization. What would you define as those shapes? Are those like some physical object?
Planar. No.
Have you guys read hybridization, sp to sp3 hybridization?
Yes, sir.
Yes, sir.
So what would you say those shapes are? What exists in those shapes?
Linear triangle.
না মানে শেপটা স্যার অ্যাটমের শেপের কথা বলছেন তো?
না মানে কি?
Sir, there are paths the electrons travel on.
Sir, these are areas which
মানে
electrons are most likely to be
Found.
মানে স্যার অ্যাটমগুলো যেভাবে অ্যারেঞ্জড একটা মলিকিউলে।
No, atom management is a different thing. That's a rhombohedral or tetrahedral, different arrangement. The hybridization is basically the shape of the electrons altogether they make, by which they can make valence or everything else. So we are talking about this hybridization is exclusive for the outermost shell layer. You should know that. For example, let's say if you do the hybridization, I mean, we are not hybridizing all the electrons, are we?
No, sir.
Yes, sir.
We are hybridizing one layer of electrons with S and P or D. D actually আমরা hybridization করি না, আমি কোন সময় পড়ি না D hybridization হয় কিনা, I'm not sure. But yeah, the reason I'm bringing it up is that these shapes are the locations where the electrons are supposed to be. These are the pathways in which the electrons are supposed to travel. They're not supposed to be elsewhere. But these shapes are the possible path in which, or possible locations where the electrons could be. Does not mean these shapes are a physical thing. Okay, electron is a physical thing, these shapes are not. Anyway, the point I'm trying to make is that whenever any electron, if the work function of an electron is, let's say, 10 joule or 100 joule?
10 joule volts.
Acha. If the work function of an electron is, let's say, 10 joule, then to make it free, we'll have to feed it 10 joule. As a result, it will become absolutely free of the attraction of the atom. Now, in technical terms, what do I mean by saying that the electron will become free of the attraction of the atom? Here's the deal. Whether let's say the carbon has an electron of 6, so we have 2, 4. So it means it has the first shell and the second shell within which the electrons exist. Does it mean it does not have third or fourth shell? The answer is it does not require third or fourth shell because there is not much electron to fill up those shells. But if you feed an electron of a carbon atom enough energy so that it could possibly exist in the third shell level, would it not travel to the third shell level? The answer is a yes. For example, let's say if the required energy of a carbon electron, let's say if the required energy of a carbon electron to travel from the second shell to the third shell is, let's say, 0.3 joule, And if you somehow can feed that electron 0.3 joule, the electron will momentarily appear at the third shell, momentarily. It would immediately radiate out that energy and reappear on the second shell. But for a moment of instance, it would appear on the third shell because it had that amount of energy access. Whenever we say that an electron being free of an atom, we essentially mean that it has traveled to a number of shell that is so large that the atom does not have any more attraction onto this thing. In other terms, we say that that shell number is infinite. This is actually a term which we're going to see in our graphs. That's why I'm bringing this up. So in other terms, I can say that whenever an electron is being free from the atom, we can say that it has traveled from its existing shell to an infinite number of shell. I can say that. Do I make sense anyhow?
Sir, এখানে shell বলতে we are referring to the energy level নাকি হচ্ছে
Yes,
the
I'm referring to the energy level, exactly.
Sir, is this like potential of gravitational potential?
It is very much similar to that. We're going to get into that as well. It is very much similar to that. So, so what I'm trying to tell you is that what wave theory predicts is that if an electron requires 10 joule of energy to become free of the atom, and if I'm going to give it energy at any rate, no matter what, it's going to start absorbing that energy, store that energy over a duration of time. And when its energy amount will reach to that value by which it could overcome, for example, whenever it's received energy amount is 10 joule, it is going to produce the photolytic effect. So in this mechanism, this is the wave theory explanation, most logical explanation. In this mechanism, there are multiple flaws compared to the actual observation of the experimental outcomes. The flaw is that, first of all, it predicts that if this is true, then photolytic effect should happen under any frequency. It's a matter of how much energy you are feeding. So if you give enough radiation, if you increase intensity, you would have photolytic effect irrespective of frequency, but that was not the actual case. That's the problem number one. So waves theory could not explain this observation. The second problem is that this explanation of wave theory, probable explanation of wave theory, predicts that there should be some time delay between the light being shined upon on the metal surface and the photoelectron actually coming out. There should be some sort of time delay because the electron should take some amount of time to absorb and store up that amount of energy, and only after which can it come out from the atom. None of these two observations were in line with the actual experimental findings. So wave theory practically failed to explain photoelectric effect. This was explained by Albert Einstein, and out of all of his amazing inventions and amazing theories and amazing creations, in 1905, he was, or 1905 or 1907, I forgot the year, he was actually given Nobel Prize because he could explain the photoelectric effect using Max Planck's theory. So what he did, he took the observations, he read Max Planck's paper somewhere, and he used Max Planck's quantum theory to explain photoelectric effect properly. So this is what Albert Einstein came up with. He said, each photon contains a significant amount of energy. The amount of energy that an electron would require to become free of the atom is a pre-given value. There is a property of that material. If the energy of the photon is equal or bigger than the work function, let's say the electron requires 10 joule, the photon which is coming by is of 12 joule. This photon hits the electron. The electron in that case will spend 10 joule of energy to make itself free, and after it becomes free of the electron, free of the atom, it would have 2 joule of kinetic energy left within itself. That is going to happen. And this entire energy transaction will happen in a single shot. The photon comes in, splashes onto the electron. The electron is energized up to a 12 joule of energy altogether at once. It is not a continuous process of energy transfer and accumulation. This is like money. You have to understand the idea of discrete energy. Money means, let's say, well, here's the deal. Let's say I'm having a fever. Let's say now I have a temperature of 102 degrees Celsius. It is impossible for me to reach 102 degrees Celsius without reaching all the in-between values. The increase of a temperature is a continuous variable. But let's say if I give you, let's say 100 taka, you become 100 taka richer immediately, and I become 100 taka poorer immediately. It's not like that I became 0.01 taka poorer first, then I became 0.02 taka poorer. It's not a continuous process. You became that much richer immediately, I became that much poorer immediately. It's a instantaneous upgrade. Do you understand?
স্যার
এপারটা কি বুঝা যাচ্ছে?
Sir, এটা কি এরকম যে like earlier the waves would live and it would just take মানে continuously হতো, আর এখন like the packets immediately transfer this energy.
Well, exactly how the light behaves is still actually a mystery. Well, what I can tell you is that the wave theory predicted that the transfer should have happened continuously, and the photon theory or the quantum theory of light predicts the transfer should happen immediately. That's the difference. These are the two different way of explanation for the same happening.
Sir, photons এর সাথে আবার frequency-টা কিভাবে linked?
How much energy would each photon have is dependent upon the frequency of that source. Or I mean, it actually quantum science they explain করতে পারবো না, but there is a physical way that I find easy to transfer the ideas to people, to the students. Let's say there is a charged particle. Assume there is a charged particle. Imagine it is as a, let's say, any color of sphere that you feel like comfortable. It's a charged particle. This is gonna move left and right. With every single movement with every complete oscillation is gonna emit out one photon. So if it is moving really at a high frequency, it's gonna emit out bigger photons. If it is moving at a low frequency, it's gonna emit out smaller photons. Try to visualize that somehow. Let's say a spherical object which has charge is moving left and right, and from every oscillation it is emitting something. If it is moving really fast, each individual photon is large. Does it anyhow make sense?
Yes, sir. So that would mean then if the frequency is higher, then each packets will have a greater amount of energy.
Exactly. That was the main proposition of Max Planck's idea, and that's what Albert Einstein used to explain the photolytic effect. So what he was proposing, that this energy transfer happens immediately, and if this energy is bigger than the work function, the photolytic effect happens. What if, and if the electron receives an energy photon that is smaller than the work function. For example, let's say the work function is 10 joule, and the source by which we are shining the light upon is delivering electrons of 8 joule each. In that case, the electron will receive that 8 joule photon. It will jump to a higher shell, but not infinite number of shells. So it will not be completely free of the atom's attraction. It will appear there and immediately come back to its original shell by giving out that amount of energy. So it will receive that energy at its original shell, jump to the higher shell, and then come back to its original shell. I might have told you earlier that electrons jump are not like physical jumps. They are like quantum jumps. Do you understand what that means? Kids?
It just pops there without moving through the physical
space. Exactly. So if an electron is taking a jump from shell 2 to shell 3, it does not travels like a spaceship. No, it vanishes from shell 2, it appears on shell 3. And if it is traveling back from shell 3 to shell 2, it vanishes from shell 3 and comes to shell 2, and all of this thing happens instantaneously. The duration of time it takes for this to happen is negligibly small, immaculate.
So, sir,
the reason is important because the electron does not stay in its higher shell for any duration of time. I'm saying it does not stay there for any duration of time. It is impossible the electron to receive a second photon in its higher shell. Let's say an atom is continuously being showered with 8 joule of photons. Is it not possible, think about it, that electron takes one 8 joule photon from level 2, jumps to level 3, then it gets hit by another 8 joule, then it jumps to the out of the atom? Is it possible? The answer is no. The electron can only receive a photon when it is in its natural or its original shell. If it is in its outer shell, it would immediately give up that energy and come back to its original shell. That's how the quantum behavior happens. That's what Max Planck proposed, and Albert Einstein used that idea to explain the photolytic effect. And according to his idea, it all made sense that the photolytic effect, if happens, would be instantaneous. So the existence of threshold frequency was explained, and if the metal piece is shined by higher intensity above the threshold frequency, more electrons would be released per second. So hence the proportional relationship with photocurrent was also explained. So everything fit into place, and it was sort of like a miraculous, what can I say, a sigh of the scientific community. Now we got an explanation that makes sense. So yeah, that worked for Albert Einstein pretty well. Yeah, Abhias bolo.
Is it like the electron vanishes and appears exactly at the same time in another place?
Yes.
Sir, so they teleport.
Bujhnei.
Sir, do electrons teleport or do they actually travel?
We, as far as our observation goes, we, I mean, this is like a spatial jump, like number 5.
Sir, Bujini.
I don't know how many of you get that reference. This is like a spatial jump, like vanishing from one place, reappearing at other, without actually physically covering the in-between space. You can say electrons do teleport, yes. In quantum science, it's called quantum tunneling. So, is it called quantum tunneling? It's the electrons actually teleport, true. And all of these things are actually happening in our body as we are having different.
So how can they
Sir,
teleport
how
without
can they
any
teleport,
system? Yeah.
actually?
We never asked the electrons. We observed this behavior as human species quite a couple of decades earlier, and we're still trying to figure out how is it possible to achieve on bigger bodies, and we
So
still
that is
haven't
like
come out
magic.
successful on that.
So sir, is it like যে ওরা যে এনার্জিটা গেইন করছে ওটা তো কোনো টাইম লাগতেছে না?
No, the energy gain is happened immediately. So the entire photon is delivered to the electron all at once, not over a duration. It's like money, like you get 100 taka recharge immediately, not over a duration of time. No. এই পর্যন্ত বুঝা গেছে কিনা?
Yes, sir.
Yes, sir.
Okay, we'll pick up more next class. Thank you very much for the additional 14 minutes of attention. Thank you. Good night.
Good.